Hey guys. So, by now you guys should have already heard a version of this lecture on Thursday. But if I didn't get to it, then today we're going to be talking about Hess's law. Hess's law. Lots of S's with Hess's. So, Hess's law. Hess was a guy. He was a guy. And yeah, we don't need to know much about him. This is kind of what we've already talked about. So on Thursday, I talked about this idea of heat of formations, that we have just a catalog of these reactions. And, these are usually theoretical reactions. Basically, you take a compound, in this case we have H2O, and we say, what basic elements make up that? And so in this case, it's hydrogen and oxygen. So yeah, you have H2 and O2 because those are your elemental forms of hydrogen and oxygen. So we put those, you put them together, you make the thing, and how much energy does that specific reaction either give off or is absorbed? So that is the rundown of what a heat of formation is. So that's what we have here. This is our delta H is, for this reaction, is negative 572 kilojoules per mole. Now, yeah, that's a fair bit. It's pretty energetic. In order to do that, it makes sense. You remember the reverse of this reaction would be a positive 572 kilojoules. So you can kind of think, well, think about like, you might have seen this before, the hydrolysis of water, basically splitting water into oxygen and hydrogen gas. You can do this just with like a 9-volt battery, like a big battery. The thing is that it's a battery. We're putting energy into it. So it's absorbing energy in order to go in the reverse direction. All right. So, and the other thing you may have noticed is this little half here. Yes, it's a half a mole. It's not balanced. It is balanced. So here's the thing. Even chemists get upset with oxygen. So when it comes to things like heat of formation, and actually a lot of different reactions, we will just go through and say, okay, no, it's a half a mole. It's a half a mole of O2. And it's fine. I think you guys are pretty used to coefficients now. I think you can handle a fraction for a coefficient. It's a half of oxygen. All right. And you're going to treat it just like any other number. All right. So there's that. Now, here's the thing. With these reactions, just like those elemental steps in kinetics, you can add reactions together. So if I have this reaction, which is graphite and oxygen becoming CO2, and I have another reaction, which is CO2 becoming diamonds and oxygen, what I can do is add these together. So I'm crossing out CO2 and crossing out O2, and then rewrite it. So carbon graphite goes to carbon diamond. This reaction, the overall reaction, since I added these guys, we just sum these guys together. So let me get my old calculator. Negative 393.5 and positive 0.41. So this is going to be a delta H of, where'd you go? 1.91 kilojoules per mole. Now, here's the thing. That's not a lot. Compared to the other things that we've been talking about, that's not a whole lot of energy, right? It's a positive number. So this means it is going to be endothermic, which means if we looked at a diagram, we have graphite here, the stuff in your pencils, and diamonds being just a little bit above it. Whoa. So what we're saying here is I can turn graphite into diamonds pretty easily, right? Right? No. Obviously not. All right. Otherwise, diamonds would be absolutely worthless. They would be just as common as graphite. Something else is going on here. What's going on here? This is the graphite, and this is the diamonds. What's missing in this energy diagram that we aren't really writing a whole lot about in thermodynamics? It's the activation energy. This thing has a huge activation energy. So we have to really put in a whole bunch of energy, and then the whole bunch of energy is released. The final product is going to be just barely above the reactants. So it is going to be one of these reactions where I'm going to put in a whole bunch of energy, but it's also going to be putting out a whole bunch of energy. So it is a fairly violent thing. There's that. We don't really talk about this activation energy step in thermodynamics, though. Again, state functions. We just care about where we start and where we end. But remember, that is not the whole story. All right, but the key that I'm wanting to get across right now is you can add reactions together. So you can take those heat of formations in that big catalog and add them together. Great, awesome. That would be useful, right? That can be pretty useful. But we can also reverse them. We've talked about this before, that the forward and the reverse reactions are going to be the same amount of energy. It's just we flip the signs, right? It's the same thing for like making and breaking bonds. If you go in the reverse, all the bonds you broke we're now making, and all the bonds we make we're now breaking if we flip-flop it. So we just change the sign. That's all we're doing. So you flip the reaction, you flip the sign. All right, so far you can add reactions together, and you just add their delta H's together. You flip the reaction, you can flip the sign. Pretty simple. Okay, let's move on. Now you can also do is multiply reactions. So, for example, here, let's say that you see this sacrilege of a half of in the coefficient. You say no. We got to double everything. So we're going to go through and we're going to double everything. We have 2 hydrogens, 1 O2 now, and 2 H2O. Well, for that, now we're going to have to double our delta H. And this is kind of makes sense if I think about like if I have double the gasoline, it's going to put out double the energy. So doubling the reaction doubles the delta H. Same thing, if I half the reaction, I'm going to half the delta H. All right. So far, so good, right? All right, we all good? Now, with all those 3 rules, we can start to do interesting things. All right. Now, let's say I don't know what the heat of formation is for methane. So we know it's going to be methane. We know it's going to be carbon and hydrogen, H2. And this is going to be my reaction. I don't know what this is, but I do have a bunch of other things. I have these. So I have the heat of formation of CO2. I have the heat of formation of H2O. And I have this combustion reaction. All right. Cool. Cool. I can use those rules that we learned before to add these all up. I just need to rearrange these guys. I can flip. I can double. I can do all that kind of stuff. So how am I going to do this? Well, what I need to do is flip this guy. That's going to be something because I need CH4 methane on my product side. So I'm going to flip this to make this on the other side. So to do that, I'm just going to put a little F there and remind myself with this big red arrow. What else do we need to do? well, we need hydrogens on the reactant side, and we got it, but we only have one here. So we're going to need to double all of this. So that's going to be 1, and that's going to be double. So what we're going to do here is we're flipping, and we're doubling this one. And I think that's good. So what I'm going to do actually is just rewrite this because it's going to be confusing in the next step. H2O goes to methane and oxygen. All right, good. So now let's just make sure that all of this adds up to the reaction we're looking for. Okay, so we need to go through and see here. We got CO2. Oh, wait, no. Yeah. CO2's cancel. That's good because it's not in our original thing here. We have 1 oxygen, 2 oxygens. Can cross out with this 2O2. We got 2 H2O. That can cancel. And what do we have left? We have carbon, 2 H's, and methane. There we go. Everything else has been canceled out. So I'm gonna really cancel these out so I don't forget. Let me double check. And we got our carbon, our 2 hydrogens, and yes, our methane, and nothing else. Everything else is canceled. Great. So we did a thing. We flipped and we doubled and we multiplied and we did all this, and we've set this up to where when we add them all together, it makes the reaction that we're after. Okay? So now we can go through and do the same thing here. What I'm going to do is flip this delta H, because I had to flip the reaction. I need to double this guy. Let me pull out good old Calcutron. Negative 285.8 times 2. And so this is going to be negative... I'm just going to move this over here so I can still see it. 571.6. Great. All right. And now we're just going to sum all of this. All right. So negative 393.5, negative 571.6, and now positive 890.3. And so this delta H is going to be negative 74.8. Negative 74.8. And there you go. That's Hess's law. I'm going to let you guys know that, and this works because, again, it's a steady state problem, right? It's a steady state thing. It doesn't matter the path we take, as long as our start point and our end point stays the same, then it's going to be fine. Let me kind of just... One sec. All right, so this is going to be a good example of what I mean by a steady state problem, right? So this is kind of a big thing, but don't let it fool you. It's the same thing. It's just kind of written a little bit differently. Let me put that down here. Sure. So what we are doing is what this means is these arrows are kind of like the arrow sign in your reaction. So if I want to say sodium solid plus 1/2 of chlorine gas goes to yields sodium chloride solid, that's fine. It's just written a little differently. And they're positioned with their delta H in between them. Okay? So, and now you can see here, there's a lot of different reactions that you can do, right? I can go straight from, the sodium and the 1/2 chlorine gas to the sodium chloride. But let's say I didn't know what this number was. geez, what could I do? Well, instead, I can say, okay, I know how to go from solid sodium to 1/2 chlorine gas. I can go this way to sodium gas. I can gas this, and I know it's going to be a positive 107. And then I take this and I ionize chlorine to where it is breaks apart the chlorine gas into just Cl. Okay, and that takes some more energy to do. And then I can go through and ionize the sodium to make sodium ions in a plus, and then it pops out an electron. I can do that, and it takes a lot more energy. And then these guys can move down here, ionize. This electron is going to get sucked up by the chlorine to make Cl minus, make a chloride ion, and that actually is going to be exothermic. We're going back down, okay? And then here, these two gases come together and release a whole bunch of energy to become sodium chloride solid. So this is just a big Hess's law problem. See? I can add all of these together. In fact, let's go ahead and do that. Oop, where'd you go? So I'm going to do 107 plus 121 plus 502, and then subtract 355 and subtract 786, and I get negative 411. All right, now let's see what that actual number was here. Negative 411. So this is just another way of viewing a Hess's law problem, except they did all the flipping and multiplying and everything for us. So that's nice of them. They're just making it a visual representation, kind of showing us the energy levels as well. All right, so hopefully that made sense. By Friday, and that's it. I have completed thermodynamics for you. That's it. So thermo's done. We will test on Tuesday. No, Tuesday? Yes, we'll test on Tuesday. Review on Monday. So I will see you guys later. Have a good one. Bye.